Hello students, we now start off with the topic of plane in 3D space. So here as shown in the figure we are having our familiar frame of reference of 3 axes, that is x, y and z, and we have shown one plane in some random orientation. Right. Now we denote a plane by a rectangle like figure as shown here, but it should be remembered that a plane is an endless surface, right? It spreads in all the 4 directions without any boundary. Now while studying the plane, we will be studying its equation, that is the way a plane is described, like we have an equation of a line in Cartesian coordinate geometry. So while studying the equations of the plane, we will be dealing with 2 forms of the equation. Right? The first form is what is called as the vector form, which will have vectors in it, therefore it's called as a vector form. And the other form is the Cartesian form, in which we will have the variables x, y and z, which indicate the x, y and z coordinates of any point on the plane. Right? So it is just the 2 different perspectives of looking at the same geometrical object, that is the plane. Alright. So let's go ahead and study the first form of the equation, that is called as a normal form. Alright. So see, in the case of a plane, we might be given different pieces of information, and based on that we have to develop an equation of the plane. So let us see the first case. By normal form, what we mean is something like this. Suppose we have a plane as shown here, and from the origin let us draw a normal, that is the perpendicular segment to the plane, and say for example let it meet the plane in point n. Okay, so n is the what we call as foot of perpendicular drawn from the origin. So I can show a unit vector, say n cap, in that particular perpendicular direction. Right? So I can call this as a unit normal vector to the plane. Now throughout the chapter of the plane, this normal vector is going to play a very crucial role. Okay, so in almost all the examples based on the plane, we have to catch hold of some vector which is normal to the plane. Okay, so keep that in mind. Now let us recap, what do we understand or what do we mean by finding an equation of the plane. Okay, so what it means is, if we consider any point, say P, lying on the plane, then we have to find out what relationship it satisfies, and that relationship has to be satisfied by any point or every point on the plane. Alright, so let us consider a random point P on the plane. Okay, now here I join point N and P. Okay, so that we will have a vector NP bar. Then the vector ON bar is already visible. Okay, so that's the vector joining O and N. Let us consider that the distance ON, that is a perpendicular distance, is denoted by small p. Okay. Here we also join origin with that particular point. Okay, so that gives us the vector OP bar. That's a position vector of point P. Now as far as the vector ON bar is considered, we can definitely write that as its magnitude, that is P, times n cap, because that's a unit vector in the direction of ON bar. Correct. So we have the P n cap as nothing but ON bar. Now if you observe the n cap, this particular vector, and the vector NP bar, they will be at right angles to each other, simply because the vector n cap is normal, that means it is perpendicular to the plane. Correct. So therefore if I take, since NP bar is perpendicular to n cap, therefore if I take their dot product, that must be clearly 0. Right? Now this NP bar, isn't it OP bar minus ON bar? Yes, we know that is final minus initial, dot n cap is equal to 0. Now OP bar we can also denote by another letter or another symbol, that is R bar. Okay, so R bar now indicates the position vector of any generic point on the plane. Right, so it's R bar minus ON bar, we already found to be P n cap. Okay, dot n cap equal to 0. So therefore on expanding we will get R bar dot n cap minus P times n cap dot n cap is equal to 0. Now being a unit vector, its dot product with itself will be of course 1. So therefore we have r bar dot n cap minus p is equal to 0, and hence finally we get r bar dot n cap is equal to p. This is what is called as the normal form of the equation of the plane. Okay, so if we look at this particular equation, that gives us all the necessary information about the plane. That means n cap indicates the normal vector to the plane, the normal unit vector to the plane, and p indicates its perpendicular distance from origin. So it's the perpendicular distance of the plane from the origin. Alright, so that is the normal form. Now let us elaborate and find out some of the important points that are derived from this particular form. So we move on to the next slide. So we have to note a few points, that is, for a plane at a distance of p units from origin and having LMN as direction cosines of its normal vector, the coordinates of foot of the perpendicular from origin to the plane are LP, MP and NP. Now this is clear from the three-dimensional geometry because its x coordinate is nothing but p times cos alpha, and the cos alpha is nothing but L. Then the y coordinate will be p times cos beta, those are the direction cosines, and that is nothing but m. And similarly for NP, which is p cos gamma. Right. Secondly, the equation of the plane then becomes Lx plus My plus Nz equal to p. Because if you recollect, r bar dot n cap is equal to p. Alright. Now r bar is a position vector of any generic point in the plane, so we can write it as definitely xi cap plus yj cap plus zk cap, isn't it? Right? That's the generic position vector. Dot n cap can be written as li plus mj plus nk, because you know that in case of a unit vector, its I, j and k coefficients indicate nothing but the direction cosines of that particular direction, right, is equal to p. So clearly when you take the dot product, you will have L into x plus m into y plus n into z is equal to p. So this is what is the equation that we have. Now taking the constant p on the left side, we get the general form, and if you multiply all the coefficients by any non-zero real number, then of course LMN will get converted to ABCs, which will be nothing but the direction ratios of the normal vector in general. And since the minus p will also get multiplied by some number, that resultant number we denote as simply d. So the important observation about the equation of the plane is that now this last equation that we obtained is nothing but the Cartesian form of the equation of the plane. Okay, so we have seen the vector form right at the top, and this is the last one is the Cartesian form. The important observation about the Cartesian form is it tells you that the equation of a plane in Cartesian form is a linear equation in three variables x, y and z, right? So that is the important point to be noted. Let's go ahead and solve one example based on this concept. Find the vector equation of the plane at a distance of 5 units from origin and normal to the vector I cap minus 2j cap plus 3k cap. Alright, so here writing in symbols, we have been given n bar. Now you see it is not a unit vector yet, because clearly 1, minus 2 and 3 are not the direction cosine. So what we have been given is simply a vector which is normal to the plane, but it's not a normal unit vector. Right? So let us still write it plus 3k. Right. We have been given the distance is of 5 units. Okay. Now as per the normal form, it's given by r bar dot n cap is equal to p. Right? We must have unit vector here itself. So since n bar is given to us, let us first calculate mod of n bar, that is its magnitude, which turns out to be 1 plus 4 plus 9 that is nothing but root 14, and hence n cap, as we know, it's nothing but n bar divided by its magnitude. So that is 1 upon root 14 times I minus 2j plus 3k. And now since we have got n cap, we will substitute in the required equation. So that becomes r bar dot 1 upon root 14 times I cap minus 2j cap plus 3k cap whole equal to p is 5. If you want, we can take root 5 on the other side, and that gives us r bar dot I cap minus 2j plus 3k whole equal to 5 root 14. So that is the vector form of the equation of the given plane. If we want the Cartesian form, what we have to mentally imagine is r bar is nothing but merely xi plus yj plus zk, isn't it? So the coefficients of I, j and k in the normal vector are to be merely multiplied with x, y and z respectively. So therefore, since the coefficient of I is 1, so therefore we write 1x, that is x. Then coefficient of j is minus 2, so therefore we write minus 2y. Then coefficient of k is 3, so therefore we write plus 3z. Right? And the constant term needs to be taken on left side so that it looks in the standard form. So therefore that is minus 5 root 14 whole equal to 0. So from the vector form we can easily write down the Cartesian form of the plane.